You click a link, and poof, a web page just appears. It feels totally instant, completely seamless, almost like magic. But in that tiny fraction of a second, an absolutely incredible journey takes place across the entire planet. So, let's pull back the curtain and follow that journey from start to finish to see how the internet actually works.
So, what is really going on in that blink of an eye? How on earth does your computer find one specific server among billions and billions of devices and get the exact piece of information you asked for? That's the core mystery we're going to solve together right now. Okay, so our journey begins exactly where you'd expect, right on your screen, with the app you're using, like your web browser. This is what's known as the top layer of something called the Internet Protocol Stack. Your browser doesn't just vaguely ask for a website. It has to speak a very specific language. And for the web, that language is HTTP, the Hypertext Transfer Protocol. It's the universal language that all web applications use to chat with each other. The moment you click, your browser drafts a formal message. It's called an HTTP GET request. The best way to think about it is like a very simple, polite letter that just says, "Hello, could you please send me the file called index.html?" This little letter is the whole reason for our journey.
All right, so we've got our letter written, but there's a big problem. We have a name, like www.google.com, but we don't have a mailing address. See, computers, they don't really work with names. They speak in numbers.
And that is where the DNS, the Domain Name System, becomes our hero. You can literally think of it as the Internet's giant global phone book. Its entire purpose in life is to take that easy-to-remember name and translate it into the numerical IP address that the network hardware actually needs to do its job.
Now, this isn't just a simple one-step lookup. It's actually a really clever game of telephone. Your computer asks its local DNS server. If that server doesn't know, it asks a root server way up the chain. The root server says, "I don't know, but you should talk to the server in charge of all the .com addresses." So then you go ask the .com server, and it points you to the final authoritative server that has the exact IP address you need. It's this beautiful cascade that lets us find any address on Earth in milliseconds.
Excellent. We have our message and we have the destination address. We're ready to go, right? Well, not so fast. We can't just throw this letter out into the digital ocean and hope for the best. We need a way to make sure it gets there reliably, with nothing missing or out of order.
And this is the job of the transport layer, specifically a protocol you've probably heard of, TCP, or the Transmission Control Protocol. I want you to imagine TCP as this super organized, slightly obsessive postal worker. It takes our big message, carefully chops it into smaller, numbered pieces, and makes a solemn promise that every single one of those pieces will arrive safely and be put back in the exact right order.
So, let's build this package piece by piece. At the very core, the heart of it all, is our letter, that original HTTP GET request. That's the actual information we're trying to send.
Next, our TCP postal worker takes that letter and seals it inside a special TCP envelope. This envelope is the key to reliability. It's got crucial info written on it, like sequence numbers, which are basically the instructions for how to piece the message back together perfectly on the other side.
So, our message is now packaged up nice and safe for a reliable trip. The next step is to put the main address on it, for its global journey, which might have to cross thousands of different networks.
This is where the network layer and the famous Internet Protocol, or IP, comes in. If TCP was our meticulous postal clerk, then IP is the massive, worldwide postal service. IP couldn't care less what's inside the package. Its one and only job is to get that package from the source IP address to the destination IP address, wherever it is in the world.
And to complete our package, that TCP envelope we just sealed is placed inside a bigger IP shipping box. This box is what gets labeled with the final from and to addresses, our IP address and the server's IP address that we got from DNS. This fully packaged unit has a technical name, an IP datagram, and now it is finally ready to travel the world.
Now, how the internet actually sends these packages is one of its most brilliant features. It's called packet switching. You see, old telephone networks would reserve an entire dedicated line just for your one call, which was super inefficient. The internet is way smarter. It breaks everything down into tiny packets or digital postcards, and each one can find its own best path to the destination. This makes the whole network incredibly efficient and resilient. Our packet is addressed and it's ready to go. But how does it physically leave your computer and get to, say, your Wi-Fi router? This is the last and maybe most physical step of its journey out the door.
That is the job of the link layer. This layer is all about the real-world, nitty-gritty stuff. Its only concern is getting our packet from one node to the very next node in the chain, whether that's moving through the air as a Wi-Fi signal, down an Ethernet cable, or through a massive undersea fiber optic line.
And for this one local hop, the global IP address isn't what's used. Instead, the link layer uses a totally different address called a MAC address. Think of it this way. Your IP address is like the final home address for the entire trip, but your MAC address is used just to find the very next person or router to hand the package to. It's a permanent hardware address burned right into your device.
And with that, it is off. Our little packet zips from your local router through your internet service provider's network and then launches onto the massive backbone of the internet, hopping between incredibly powerful routers at nearly the speed of light.
Finally, after its long journey, it arrives at the destination server. The server unpackages everything, layer by layer, reads our little HTTP request, and then it does this entire process in reverse. It takes the web page data, packages it up in exactly the same way, and sends it on the return journey all the way back to you.
So when you really step back and look at it, it's not magic. It's a symphony. It's this beautifully coordinated dance between all these different layers of protocols where each one has one very specific job to do, and it does it perfectly.
So let's recap our analogy one last time. The application layer writes the letter. The transport layer puts it in the reliable envelope. The network layer puts that envelope in the globally addressed shipping box. And the link layer uses a local mail truck to get it to the next post office. Each layer just hands off its work to the one below it. It's an elegant and incredibly effective system.
You know, this whole incredible architecture really is the fulfillment of a vision from one of the internet's pioneers, Leonard Kleinrock. The goal was to make it all invisible, to make it just work. And the fact that we can do all this with a single click, that it feels like magic, is proof of just how wildly successful that vision was.
And that leaves us with a pretty amazing final thought. This fundamental design, this layered approach, is decades old. It was invented when the internet was a tiny research project. So what is it about this model of separating one massive, complex problem into a series of simple, independent layers that has allowed it to scale up and power our entire interconnected modern world?